Okay, today we are looking at matter and classifying matter and separating techniques for matter. It's a pretty short little lecture. Again, it's a review of some Chem 1 concepts. Up here on the video, it's kind of hard to read, but on your handouts, you should be able to read the words a little bit better. So we know matter is pretty much everything around us, and matter is composed of two different kinds. We look at things as either being mixtures or as being pure substances. So we can classify everything in one of those two categories. So let's look at the pure substance side for a second. Pure substances include just atoms by themselves or the combination of atoms in a set proportion. Those are pure substances. So when we're dealing with these compounds, the composition can't be variable. We have a set amount. If we have sugar, C6H12O6 is always C6H12O6, right? Okay. So the difference then with mixtures are our mixtures, which are two different categories, can be in any proportion. We can have a lot of salt and water or a little salt and water. And then we have our two types, our heterogeneous and our homogeneous mixtures. Can anyone tell me the difference between the two? Go ahead, Roy.
So heterogeneous mixtures are ones where you can tell the different things making up the mixture.
Okay.
Homogeneous mixtures, you cannot tell. It's kind of blended.
Kind of blended. Right. Homogeneous mixtures look blended, meaning there's one phase. If you were to take a spoon and take a spoon of homogeneous mixture and then another spoon, they would look identical. Okay. So this is one phase. Usually things are soluble in each other in homogeneous mixtures, okay? It's when things aren't soluble, when you have they're immiscible. The word of not being able to dissolve in each other is immiscible. When you have two liquids that are immiscible, you get layers. And things like that are what cause things to be heterogeneous. So can we give me some examples of some heterogeneous mixtures? Naira? Did I hear watermelon? Water and oil. Oh, I was like, God, watermelon sounds so good right now. Yes. Yeah. Soil, yes, is heterogeneous. Yes. Fruit salad is. It's so funny how people go to food most of the time. Or food are like, can anyone think of any chemical mixtures? Well, water and oil is kind of a chemical mixture. That would be heterogeneous. In the chemistry world, anything? Too much chemistry. Oh, yeah, okay. Yes. Water and bromine, very good. That was in yesterday's graduated cylinder example. Okay, Kate. Never mind. What about homogeneous mixtures? We can do a ton of those in chemistry. Salt water, sugar water, hair, air. Oh, air. I thought you said hair. I was like, well, hair is a mixture. Yes, air is one of the consummate homogeneous mixtures because it's all evenly distributed and spread out. So that was a good one. Air is also known as a what's a homogeneous mixture also known as? Solution, yes. Can anyone give me an example of a solid homogeneous solution? Naira. An alloy. Give me an example of an alloy. Bronze. What else? What about in your real life? When do you see that? What? Right. When do you see that, though? When, like, do you have a block of stainless steel at your house? Well, jewelry, when it's plated, isn't really considered homogeneous. Now, an alloy, like a bronze jewelry, would be. What about, are any of y'all cyclists? These bikes are made of different mixtures, different alloys. Golf clubs, alloys, yeah. Brass instruments, there we go. Go band and orchestra, woo! I thought I'd hear a good yell for that. All right. Okay. So yeah, what about a heterogeneous solid mixture? Any ideas? Heterogeneous solid mixture. Granite, nice. Yeah, that granite's perfect. That's pretty much what I was thinking. The sand with the... Oh, yeah, nice. When you mix sand and iron, and you can separate them with a magnet. Yeah, nice. Okay, granite was the thing that was in my head because it's like it's a set piece of rockish thing that has different components, and it's not Two slabs of granite. I mean, ask my friend across the hall. She just had her kitchen done, and yeah, not really happy with the slab that she got compared to the one she saw. They look totally different. So yeah, definitely heterogeneous. Okay, so are we comfortable with this kind of thing? Yeah, Naira. Blood settles out, and the fact that you can well, that's really tough. It's a before and after thing. When you take it from your body immediately, it's definitely homogeneous, but when you let it sit, that's one of my Department of Health stories that is really gross. So you're going to hear one, because all my pre-APs heard this last year, what I did as a job. But another part of that job, the first 6 months there, I was at the Department of Health after I graduated as a chemist. And the first 6 months, they make everybody work in check-in. And check-in is where every sample that goes to every department in the entire Department of Health goes through, and you put a number on it and all this kind of stuff. So part of my job was to check in blood samples. Oh my God, apparently people like to give blood like after they have McDonald's for breakfast or something, because the blood separation was so disgusting. It was the red blood cells, and there was fat, just clumps. So this is coming out nice and stream-like from people's bodies, but then you let it sit, and this fat just like separate. I did not eat fatty foods for like 6 months after I left that place. I was so disgusted by it. And then it's like, that's what clogs your heart. That's what gets in all the arteries and makes people die. And oh my God, it was horrible. So yeah, that was bad. They did rabies tests there. So guess what I got in boxes? Dog heads. Because you have to do brain checks. You check the brain matter. Yeah, I didn't actually test that, but not fun. Not fun. Checking in Pookie's head. Not my idea of a good time. No, I didn't Yelp about it. I didn't have the Yelp app back then. That was a long time ago. This is my 19th year teaching, so that was 20 years ago. Yeah. We didn't even have iPhones. My cell phone was that baby flip phone, and the text you had to hit number 1 3 times to get to the C. Oh my God, that was horrible. Yeah, and you definitely couldn't text and drive because you'd kill. That's what they need to do. All iPhones, when you're in your car, revert to the old way of texting, and you would not be texting and driving. Yeah, now on the Samsung and all the Galaxy stuff, how you can just like scroll your finger and not even the swipes. That's crazy. That's kind of cool. I kind of wish the iPhone did that. You can? I'm so tired of downloading things right now from our stupid iPads. I'm tired. All right. Okay, let's talk then and look at these. I'm not going to, this before we move on. So one thing that you guys might be tasked with this year would be doing drawings. And I'm not going to actually have you draw right now, but I just want you to see how things can look. When we ask you to draw atoms, we don't want you just to draw, oh, this is sugar. No. They have to be more symbolic of what is actually there. So your atoms would be single little balls. Your compounds have to be not only, what do you notice about this water molecule? The way they drew it. It kind of has the shape in there, right? That bent shape, that water. So that's the level that we want. So when you're asked to do these things, you really need to take your time and say, does that kind of represent to the best of my ability what water actually looks like? Okay? And then, you can't just say, oh, this is oxygen. No, oxygen has 2 atoms naturally as O2. So again, that's the level of expectation. And then here they're showing you might have to do reactions. And if you draw reactions, what's important is, here we don't have one water making 2 hydrogens and a diatomic hydrogen and a diatomic oxygen, because that's not balanced. So notice that this is kind of representing a balanced equation. So oftentimes on the AP, they'll give you pictures, and they'll say, is this possible? And you'll be counting, oh, no, that's an excess, and you're counting these. And you might have to sit there and count 25 balls to figure out if it's a balanced equation or not. So again, a high level of detail. And then here is just an example of what they do with phase changes. Sometimes in these they're called particulate diagrams. Here you can see this solid versus this is ice, and then this is liquid water. Do you see the difference there? You see how this is superstructured? What else do you notice? Anything? That's structured, but this is like a little bit looser. Yeah, definitely looser. Versus this, what does that little tail mean? Yeah, they're moving fast. So little tails mean fast, move fast. So these, what's also important though, more so than the tails and the movement, is the number of atoms in the same set area. What does that indicate? This is the same amount of area as this. What does the fact that I have only 2 in here indicate? They're really spread out. Gas molecules are really spread out. Again, another detail you might not think about when you're drawing things, but that's kind of where we're at. We want to use these drawings to make sure you really conceptually understand about matter. So you're going to see these and definitely remember what these are. You've seen these exact ones before last year or the year before, depending upon when you took chemistry. So we're going to classify these in different categories. I'm going to do a couple with you and then just point out ones you think you need help on. I don't feel the need to do all of these. Category 1, homogeneous, heterogeneous, or pure. What is A? It's a pure substance. Elements, compounds, or both? Just an element, right? Solid, liquid, gas, or combination? Just a gas. That is correct. I guess I should write it down for the video while I'm doing this. So we said pure, element, and we said gas. Okay, the next one, B is weird. I don't like the fact that there's 3 here. We're going to pretend these are just 2 balls, like a diatomic, okay? Get rid of this 3 thing. I'm not happy about that. Dumb. Okay, so those are diatomics down there. Number 1, heterogeneous, homogeneous, or pure? This is definitely hetero. Why is it hetero? See this? The question you ask yourself is, could I mix that up a lot better? Yeah, you could. If you can mix it up a lot better, it's definitely heterogeneous. Element, compounds, or both? Definitely both. We know that this is a compound. It could be water, right? But these are diatomics, and diatomics aren't considered compounds because it's the same thing attached. It's just 2 of the same, so those are considered elements. Elements. Now let's talk about the phases. What do we think's in there? It's obviously a combo. What's the combo? So with these pictures, if it's at the top, it's definitely a gas. Okay? So this is a gas up here. Now the question is this solid or liquid? It's a liquid. Why? This is what a solid looks like down here. See the difference? Those are kind of free flowing. They look looser. They're not as packed, and they're not little military regime looking as these are. Okay. So I think you all get it. So now I just want you to throw out a couple that you have questions about, and I will work them. Yes, Abby. Is D homogeneous or pure? Well, what we have in there are compounds, right? And they're all the same. Since it's all the same compound, those all could be sugar molecules, or they all could be acid molecules, or so that would be pure. It's not a mixture. D is not, it's a good question. D is not a mixture because it's the same substance. Yes? I would say C is homogeneous. I can't very readily draw a line to separate them. So heterogeneous, sorry. I said the backwards. I say homogeneous. They're homogeneous because I can't draw a line to separate heterogeneous parts. Isabel? Is J hetero? I would say J would be homogeneous as well because these diagrams tend to do their separation in an up and down fashion. So I know you can do this, but I still say it's homogeneous. Yes? I would say I would be a liquid and M would be a solid. So these two are identical, except this is a liquid and that one's a solid. You see the difference? Okay. Rui, did you have one for me?
Yeah, it was about
J. Okay. Yes? Yes, I think L is a good hetero example. Because, and this is kind of even more realistic because stuff isn't straight across. Due to attraction to the sides with capillary action and that kind of thing, we have concave and convex situations where this thing is attracted to itself, so it will make a concave. So this is a really good example of a heterogeneous mixture. Yeah?
So would L be a liquid?
L? Yes. L, no, where's L? Yes, L is a liquid. This would be two liquids. I don't know, I saw this L and it threw me. It made me think that's what we were talking about. This is two liquids, yeah. Any others? Can anyone tell me what the compound is, the formula for the compound in O, and why? Look at what's going on. Yes. Your last name's Whaling. What was your first name? Matthew. With a K. Matthew Kearney? Okay. What did you say O was? This, okay, oxygen is a di... Oh, no. I want to know what O is. Carbon dioxide is the answer. Why is that carbon dioxide? Something very specific about it is making it sublimation. What does that mean, JD? And that's what's happening there. You have this carbon dioxide as a solid, and all of a sudden it's gaseous. So the two phases there are solid and gas. So that would definitely be CO2. And it even matches with the little balls, C in the middle and the O's on the outside. Sublimation. Sublimation. Okay, y'all feeling okay about these? All right, now we're going to talk about how to separate mixtures. We don't talk about how to separate compounds because it's really hard. It's not something we can easily do in laboratories. It requires lots of energy. If I wanted to separate water into its components, I'd need to shoot electricity through it or do something. Because even heating water, does that separate water into its elements? No, what does heating water do? Just phase change it, and then the gas molecules just keep going. So it's really, really, really hard to separate compounds, so we don't even talk about it. What we do, though, is talk about how to separate mixtures. So on the AP, you're going to have to talk about a lot of different techniques, and so since we're just talking about matter, we're going to look at the techniques for separation that we can do here. The first one is decantation. This is the in the alley kind of separation. You can do this anywhere, and you probably do it very commonly in your life. Can anyone describe decantation to me? Myra? Yep, when you pour off something that's on top of a of some sort of mixture. You can gently pour off even two liquids. If you have a really dense liquid and a less dense liquid, you can kind of pour some off. If you have rocks and water, you can pour off the water. When you cook spaghetti and you pour through a colander, that's kind of like decanting, sort of. You're pouring off stuff. Well, not really, because the colander, you're dumping the whole thing, so no, that doesn't count. Ignore that. But anyway, so what kinds of mixtures would you use this on, though? Heterogeneous, homogeneous, or both? Yeah, this has to be heterogeneous. Can anyone tell me some drawbacks to decantation? Yeah, if you mess it up, you got to go back and do it again. Contamination of the other, meaning? Well, you're going with an empty thing and you're pouring into it, so there's nothing here to get in. So what do you mean? Yeah, so say you had rocks and water, if you pour the water, it's going to be almost impossible to get all the water over. There's going to be some left behind. So this is kind of a quick and dirty thing. You guys did this in qual all the time. When you were centrifuging and pouring off the wash water in your qualitative analysis unit, that happened quite a bit. All right, filtration is next. Filtration, when you make coffee, it's based on filtration. You have the coffee grounds and you're running water. It's kind of a backwards filtration, but no, it's not, actually. You're pouring water into the coffee and the coffee's staying and the water comes through along with some awesome caffeine dissolved in it. It's the best. What would filtration be good for? What types? Marie? solids and liquids, yes. So what type of solution is that? Yeah, we're best off for that kind of thing. Some could argue if our filter, whatever we filter through, is tiny enough, we could potentially separate homogeneous mixtures, but it's really, really rare. So we're going to stick with this being good for only heterogeneous mixtures. So let me ask you, what are drawbacks to filtration? Are there any? Not getting completely? Yeah, I mean, some stuff will actually kind of stay behind in the filter to a degree. And the fact that, this could be a lot better if we did some other things to it to make it good for homogeneous mixtures, but all in all, it's not a horrible way. It's definitely way better than decantation. Okay. All right, let's go on to the next one. Evaporation is next. What is evaporation? What do you have to do to evaporate something? Heat it. So can someone describe what's going on? Let's say I put salt water in that evaporating dish. I put H2O that has some Na plus and Cl minus floating around in there. Okay, louder, Kate. The H2O is going to leave and the solid stays. Why is the H2O leaving? Why? We're heating it and it's changing phases, right? It's going from it's going from liquid straight up to gas. What would be the main obvious drawback of this? Not missing some. You can't collect the water. You're losing. It depends on what you're trying to do. If you're trying to desalinate water so you can drink it, is this the method you're going to use? No, it wouldn't be real smart because your water's gone, right? So that's the main drawback. We're going to lose our solvent, and our solute is going to stay behind. This is great for harvesting salt from seawater, but not for the drinking water itself. What kind of mixtures should we use on this? Homogeneous? Either. You could do rocks in water. It would work. We dry those off. Okay, so this is for both heterogeneous and homogeneous. And you notice I say homogeneous and homogeneous just because I can't decide what I like better, and potato, don't care. All right, distillation. Distillation is when you get to hear my other Department of Health story, unless some of my pre-AP students from last year want to tell it. Do y'all remember my meat story? No? Oh, yeah. The spider story is good, yeah. And you will hear the spider story again. Actually, no, we don't do half-lives in AP Chem. No. Okay. No, we're not today. We got to talk about good decision-making. So, hold on. But what we will talk about before that is what I did before So, after I spent 6 months in check-in dealing with gross blood and dogs' heads, I was sent to my primary lab where I did first water testing for a while, drinking water. Then I did some wastewater, which was just as nasty. And then I did food. And food is what pushed me over the edge, and I ended up leaving and saying I just really would rather become a teacher. So what I was in charge of testing was to verify labeling on ground beef. So when you buy ground beef, you often see 95% fat-free. So they're supposed to be 95% protein and 5% fat, like that 80-20, you know what I'm talking about, right? So we'd get samples from all over the state that had been randomly selected by EPA to be tested. So the first problem was they'd ship this stuff in a non-refrigerated, in a non-refrigerated truck, and then it would sit in check-in for a couple days, and then it would eventually show up to me. So imagine what I was smelling when I was opening this plastic. And then you can't use the outside because it's you got to get in the middle and get the pink in the middle because the outside's all disgusting. Yeah, it was bad, y'all. I can't even tell you. So then I had to take the meat and put it into a grinder that had really, really, really fine holes. So when it comes out, it was like a paste. So it looked like pink toothpaste, but it was like meat paste. So you had to do that to get it homogeneous and to get it more surface area, it would react better. I'd get better results. The more I ground it, the better my results were, right? So what I'd use would be this distillation apparatus. What the distillation apparatus does, it's evaporation on this end. So you have a solution, it evaporates. Some of it stays, the solute stays behind. The solvent goes up here and goes down this condensation tube. Water will go in and out attached to a sink. So I had a hose running from a sink here and then another hose running into that sink. So I'd have cold water circling this inner tube. The hot gas from here goes into the inner tube, and when it hits it, it recondenses because it's cold. And then it drips into here. So it's a way to save both portions. So if I were to desalinate water, this probably would be how I do it. If I were to purify moonshine, this is how I do it, because all the impurities stay behind. All right? So it gets stronger and stronger and stronger for every mill because we're getting rid of all the impurities. But you don't need to know anything about that. That's good. So, good decisions. See, we can tie it into everything. All right, so what I did was I would weigh this. This is called a Florence flask, the round bottom flask. It's not an Erlenmeyer. It's a Florence flask. And I would put, I knew the mass of the Florence flask, and then I put in maybe about 1 gram, I'm just giving an example, of the meat paste. And then I just top it off with some sulfuric acid. Does anyone know what sulfuric acid does to protein? It denatures it, right? So the protein gets denatured and it dissolves into solution with the sulfuric acid. It becomes a homogeneous mixture. And then what do I have floating in bubbles on top? The fat. The fat. So then I heat it. The sulfuric acid protein mixture ends up here. So in this one I have protein, denatured protein, plus sulfuric acid. What's left behind? Just fat. So I'd go weigh the Florence flask again, subtract the weight of the flask. I know how many grams of fat are left behind. So if I have 0.5 grams of fat and 1 gram of stuff to start with, what's my percent? 50% fat. So I could figure out the percentage of fat. Now, you think that would be enough, but no. I have to then take that sample. So I'd run like 20 samples like this. That would take me a day. And then the next day I'd come and run those same 20 samples via titration to verify how much protein. So my protein and my fat had to add up to 100%. I could only be plus or minus 0.5% in order for it to pass. If I wasn't within 0.5, like 99.5 to 100.5, I had to rerun, which pissed me off. So, yeah. It was lots of fat. For food, I also tested for yellow number 5, which is a bad food dye. You're not supposed to have that in our foods anymore. And most of our stuff that came from, we did get some samples from border towns that, yeah, there was yellow number 5 everywhere. So, yeah, and that wasn't as gross. That was actually kind of cool. You took candy and you dissolved it in ethanol, and you just did spectroscopy and ran light through it, and you should see peaks. The yellow number 5 peaked at a particular wavelength. So you run it all through all the wavelengths, and if you see a peak at a certain wavelength, you're like, oh, that's number 5. Shouldn't be in there. So, yeah, it's cool. That was cool. And it was candy, and usually lemon drops. It was, like, awesome. Even though I never ate them, I wanted to. All right, so distillation. What types of mixtures would that be good on? Both. All right, and then finally we have paper chromatography. In paper chromatography, this is only good for homogeneous mixtures. You guys did this with Kool-Aid at some point, where you had your filter paper, you put a dot of Kool-Aid, you made it really, really dark, and then you put it, and then you put it in an eluent, and it went up and it separated its colors. The point of this, it has to be in the same phase. It's not going to dissolve and move if the polarities aren't the same. So it has to be homogeneous. This is kind of not a great chromatography. Chromatography in itself, there's lots of different kinds. And we're going to be doing one kind this year that's different than this. But there's chromatography. When I was at UT, I was a biochem major, and I was separating DNA strands. After putting a restriction enzyme into some DNA, it cuts the DNA into different size strands. And so by running it through a column, I could collect the small strands first and then the bigger strands later. And so we'd run a timed machine holding test tubes. The columns were taller than me. You'd go put the sample up top and you'd run this thing, and every 5 minutes it would turn and you'd collect a different size strand of DNA. It's really cool. So this was called size exclusion. The bigger it is, the slower it traveled. So this is very complicated, and we're going to do one kind at the end of the year when you guys have more chemistry under your belt. But all right, so that's it about all of this mess. Any questions on this stuff? Okay, I'm going to turn off the recording, and we're going to start talking about good decision making.